So last time we started to talk about the about cosmology, the Robertson-Walker space-time, and the Friedmann equations. So today we will talk a little bit more about the implications of cosmology, and we will also start looking at what it means for our universe when we start filling the universe with different things, and looking at the history of our own universe. And finally, we will be discussing cosmological inflation, which is only included in the larger SH course. And we will be discussing why there could have been inflation, why we think there might have been inflation, and what might have caused it as well. But what we should remember here is that inflation is a rather theoretical subject. We have not actually found any conclusive evidence for inflation. It's just a very nice solution to several of the problems of the standard Big Bang model that we will see. So let's first take up the concept of what is often called cosmological redshift. I'm going to put cosmological in quotation marks for reasons that we will see later, which is essentially, well, you know, the fact that if you look at the cosmic microwave background, you may have heard that this is a remnant from the early universe, when the early universe essentially became transparent to photons. And you might have heard that the temperature of the CMB today is around 2.7 kelvins. Of course, it was much hotter at the time when it was released because the universe was much smaller. And the reason for this is that the photons of the CMB have been redshifted over time, so they have become less energetic with time, let's say. And this is often referred to as, or referred to be caused by what is called cosmological redshift. Now, the reason I put cosmological in quotation marks here is that a priori there is nothing telling you that this is something particular to cosmology. You could always go back to what we did in one of the earlier lectures and just say that redshift or frequency shift in general is just based, you have an observer emitting the light signal, and you have an observer receiving the light signal, and then you have the space-time, and the space-time geometry essentially tells you what the observed frequency is going to be. You can do that argumentation here as well, and there is no need to kind of refer to motion relative to the cosmic frame or anything like that. But when we talk about cosmological redshift, we are typically talking about the redshift observed in light emitted by and observed by two co-moving observers. So observers at rest relative to the cosmological frame. So the idea is the following. So we consider two co-moving observers. So again, this means that those two observers are going to be stationary at the same spatial coordinates. So if I draw us kind of schematically here, if I draw the diagram, we put the t-axis on the vertical axis, and we put the spatial distance in the horizontal axis. Let me call it r actually, because we can, given two observers, we can always arrange our coordinate system in such a way that the path between them is a radial path in this cosmological Robertson-Walker metric that we have seen before. So I'm going to put the observers at R1 and R2, and since they are co-moving, this just means that they are always at the same spatial coordinate, which again means that their world line will have a tangent vector, so the forward velocity will always be just u equal to dt. Okay, and then the question is, I have this observer at R1, and this observer emits a light signal, or rather two consecutive light signals. You can see them as two consecutive light signals, or two consecutive wave crests of the same wave. So I'm going to draw that something like this. So we send something out like this, and we send something out like this. Actually, let me do this instead. Let me draw it like this. So a priori, we don't know exactly how they're going to go. We only know that we have also here a scale factor that depends on the cosmological time t. That's of course in all of the space-time. So inside here, and that's essentially going to determine how these light-like geodesics behave. And I'm going to call this here the difference in time. If I look here, this time I'm going to call delta t1. So the difference of the time of the emissions of the consecutive signals. And the same thing up here, but this might a priori be a different time, delta t2. So that's the difference in the time coordinate between receiving those two signals. Now they don't have to be the same in general, which is of course why we have this redshift. So the question is now, given this delta t1, what is delta t2 going to be? So if we now have assumed now, or rather we have arranged our coordinate system such that this path here is completely radial, so we can forget about any angular coordinates. And again, there's always a way to arrange that such that this path from R1 to R2 is purely radial. Then if we look at the metric, then we will have that ds squared is dt squared minus a of t squared dr squared. So again, we forget about the angular part and we just look at the radial part. But for a light-like signal, this has to be 0. And if we assume that R1 is smaller than R2, then both dt and dr have to be positive. So this will then imply that dt is a of t multiplied by dr. But this is separable now. So what we can do is the following. We take the a of t to the left. We divide here by a of t and integrate. And we integrate on the right-hand side, we will only have dr. Let's write it down. So we do the following. dr is dt divided by a of t. So the right-hand side depends now only on t, and the left-hand side depends only on r. So what I'm going to do is that for one of those light signals, I'm going to integrate here. If we take this time to be t1 and this time to be t2, I'm going to integrate here from t1 to t2. But in the radial space, that corresponds to integrating from R1 to R2. But I can also do exactly the same thing for the second light signal, except that then integrating from R1 to R2, that's going to be equivalent to integrating from T1 plus delta T1 to T2 plus delta T2 of the same thing. So we now have this equality. So for both of those signals, those integrals have to be the same. But I can now take this integral and move it to the right-hand side here in this equality. And what we will see then is the following, that we have this entire range of times between here, where this integral cancels out this integral. So what we will be left with is, on one hand, the integral from t2 to t2 plus delta t2 of dt divided by a of t, minus the integral from t1 to t1 plus delta t1 of the same thing. And if we now use that, well, we're going to assume that this delta t1 and delta t2, that those are going to be small times, which means that we can approximate those integrals. So this should be equal to 0. We can approximate those integrals by the length of the interval, delta t2 in that case, and delta t1 in that case, multiplied by the integrand. So this is going to be approximately delta t2 divided by a of t2 minus delta t1 divided by a of t1. And since this should be 0, we can solve for the ratio here between delta t2, or rather let me solve for the ratio between delta t1 and delta t2. So that should then be equal to, we take this and we put it upstairs, we take this and we put it upstairs there. So it's a of t1 divided by a of t2. So this is the ratio between the time difference here, the time difference here, is given by the ratio of the scale factor at each time. However, we were interested in the frequency. So the frequency observed at R1 is going to be F1, which is going to be proportional to 1 over delta T1, because the frequency is proportional to 1 over the period. And correspondingly, F2 is proportional with the same proportionality constant to delta T2. So this means that if I insert that here, what we obtain is that the frequency at R2 divided by the frequency at R1 is the opposite quotient. So 80, well, it's the same quotient, but opposite meaning of 1 and 2 here with respect to here. So A of T1 divided by A of T2. So if we have a scale factor at the emission of this signal, which is smaller than the scale factor when we receive the signal, then the frequency at reception is going to be smaller than the frequency when we emitted the signal, which means, of course, that that would correspond to redshift. So if A of T1 is smaller than A of T2, then the signal is redshifted. Now, this condition is, of course, telling you that if the universe expands from T1 to T2, then you have a redshift. If the universe would instead contract, so the scale factor will become smaller, then we would have a cosmological blue shift instead. But since the universe we are living in is expanding, we are typically talking about cosmological redshift. So I just want to mention one thing with regards to this, and that is if you look in papers on cosmology, for example, you will often see that this means that cosmologists will often take redshift as a time surrogate. So redshift used as a time surrogate. What you will do if you look at things, if you look at the relationship between Z, which is the redshift parameter, and T. So Z here is typically defined as the emission frequency divided by F, the observed frequency, minus 1. Then you will find that this is 1 divided by A of the emission time minus 1. And here we have taken A of T0. No, this is F0. Sorry, I confused things. F0 is the, yeah, so in cosmology, I forgot to say this. T0 is often used to refer to the time today. So if we are the observers, F0 being the frequency at T0 is the observed frequency. And this A of T, the T would be the time of emission. And also we are often defining that A of T0, so the scale factor today, is often taken by convention to be 1. So if we do this, then we can plot this redshift as a function of time, and you will see that it goes down like this monotonically, as long as the universe is expanding. So for example, if I would say that that if a cosmologist say that they observe something at redshift 10, say, then that what they are saying in actuality is that take the point where Z is equal to 10, and the time they are referring to is the corresponding time here on the t-axis. So larger Z means at earlier times. Right. Any questions? If not, let's go on and discuss the evolution of our own universe. So the evolution of the universe. So if you look back to the Friedmann equations, just remind ourselves here. So these were the Friedmann equations. We had this equation, and then we had the equation for the Hubble parameter. So these are the two main equations that we use in cosmology. If we look at those equations, we see here a quantity which is 8 pi g multiplied by the energy density divided by 3. So what is common to do, and we see that also that on the left hand side here we have the Hubble parameter squared. What is common to do is to introduce what is called the critical density. So we introduce the critical density as rho c equal to 3h squared divided by 8 pi g. So why is this called the critical density? Well, if you look at the Friedmann equation, let me actually copy the Friedmann equation from here. If we copy this Friedmann equation, if I would insert into this this critical density for the density, then I would get 3h squared divided by 8 pi g. So the constants would cancel the constants here, sorry. And we would be left with h squared there, and we would have h squared on the left-hand side. So this would mean that this term would be equal to 0. So that would mean that we would have a flat universe. So the critical density is essentially the density for which we have a flat universe. Then we can also define the density parameters. So in this case, if rho is equal to rho c, then this curvature parameter kappa is going to be equal to 0, which would mean that we will have a flat universe. What we can do is that we introduce a density parameter. Also introduce the density parameter of a fluid as omega for the fluid being equal to the energy density of that fluid divided by rho c. If we do this, then the Friedmann equation for h squared becomes the following. So it becomes that 1, which comes from essentially dividing here by h squared. 1 becomes equal to the sum over I, where we sum over all the fluids that are in this universe, and we sum over the individual density parameters, and then plus what we call omega kappa, where omega kappa here is the is depending on the curvature. So this is going to be equal to minus kappa divided by h squared a squared. Now we know how each individual fluid component here, or rather how the energy density of each individual fluid component is going to behave. So we know since before that rho I, so if I take fluid I and I look at how that fluid behaves, then this density is proportional to the scale factor to the power of -3, 1 plus Wi, where Wi is the equation of state parameter for the fluid. We also went through this last time. Let me see if I can find it just briefly. Yeah, so this was this, we discussed the behavior of this ideal fluid. And we found that we had this kind of behavior when we had an equation of state parameter W. Now we might have several equation of state parameters for different fluids, but the idea is the same, and we get that the energy density is going to scale like this. So this means that we're going to be able to write down now a general differential equation starting from this basically, or equivalently from this. And if we do that, we can write down this Friedmann equation on the following form. So we will have a dot divided by a squared on the one side. That's going to be equal to 8 pi g divided by 3, and then the total energy density. Let me make here the assumption that we are in a flat universe. So assuming a flat universe, so that means that omega kappa is equal to 0. And then I insert all of those energy densities And the total energy density is, of course, the sum over all the individual energy densities. So I'm going to take rho 0I, which is the energy density today of this component, of this fluid. And I know how it scales. And assuming that the scale factor today is 1, then we get 3, 1 plus Wi here. And I can here solve for A dot and obtain that A dot is square root of 8 pi g over 3, and then the square root of this entire parenthesis with or this entire sum. So rho 0I A to the minus 1 minus 3 Wi. So what I have done here is of course I've taken this A squared and put it here essentially. And then you get this differential equation. So this differential equation essentially tells you all you need to know to solve for the scale factor. So this is the time derivative of the scale factor. And here on the right-hand side, you have something that only depends on the scale factor itself. So if you know all of the density components today, then you can solve for how the scale factor has behaved historically, essentially by integrating this equation. So let's take an example of that. Now, of course, it's not necessary then that this differential equation is analytically solvable. And in many cases, it will be, or it will be expressed in some hypergeometric functions or something like that. But in general, we might not have a simple solution. But in this case that I'm going to take the example of, there is a simple solution. So this is the one component matter-dominated universe. So that is to say we only have one fluid, so only one fluid with W equal to 0 because we want a matter-dominated universe, and matter or dust corresponded to the equation of state parameter W equal to 0. Now flat will imply that the density today is going to be equal to the critical density today. So we know what the density will be at the current time. So then we can go to this equation. Let's take this equation. Let's actually copy it and see what it becomes. So we have here this. Now, A dot we leave as it is. That's going to be equal to the square root, and now the sum is just has a single term. It's 8 pi g rho 0 divided by 3. And then we have A to the power of, well, W was 0, so we only have, and then we have a square root, so it's minus 1/2. Right? So we move here, this A to the 1/2, we move to the left-hand side, and we move the dt of this derivative to the right-hand side. So what we find is that dt and this entire square root, let me take it like this, 3 divided by 8 pi g rho 0, that has to be equal to dA multiplied by the square root of A dA, right? So what I'm going to do now is that I'm going to take this from time t equals to 0 to some time t. Never mind that I already used t for the integration variable. I'm using a bit of Boston notation here. And then on the right hand side, I should integrate from a at time 0, and let's put time 0 to be the time where we have scale factor 0. And I integrate to a of t. Then on the right hand side here, I have the integration of a square root. So what I get out of this is 2/3 multiplied by a to the 3/2. So that's what I get from the right hand side. From the left hand side, well, I just get this square root of 3 divided by 8 pi g rho 0 multiplied by t. Now, this thing here, if I just consider the fact that rho 0 was equal to the critical density today, then this entire thing, this entire square root, well, what's inside the square root is
sorry, I think there's a mistake in the last line. It should be dt times 8pg rho over 3.
It's possible, yes. Let's see. So I go from there. Yeah, you're right. It should be 8 pi g rho 0 divided by 3. The same thing here. 8 pi g divided by rho 0 divided by 3. So the point is that if I insert now the definition here of the critical density, then what is left here is going to be just the Hubble constant today. So what we are left with is h0 multiplied by t, which means that I can now solve for the scale factor a of t, and what I will obtain is, well, I need to multiply by 3/2, so it's 3h0 divided by 2, and then multiplied by t, of course, and then this entire thing to the power of 2/3. So in the case of a matter-dominated universe, you will have the following kind of evolution. So you will have this scale factor evolving as proportional to t to the 2/3. And you can make similar arguments for example, radiation dominated, when W would be equal to 1/3 instead. Essentially, this differential equation, if you only have one component with a given W, it's relatively easy because you'll just be integrating something that's some power of A. The difficulties come instead when you have something that's not a single component, because then you will have several contributions here. So you'll have a sum of different terms. And then your integral will generally become a bit more tricky. So in the case of a radiation-dominated universe, for example, there's an exercise in the lecture notes, which is to show that in the case of radiation-dominated, you actually get that this, instead of being proportional to t to the power of 2/3, it's proportional to the square root of t. The last thing I wanted to discuss in relation to the SI course, and then we will continue discussing inflation in the SH course, is accelerated expansion and the cosmological constant. Cosmological constant. So you may have heard, it was now like, I guess it's some time ago now, that that there was some buzz in the community, in the scientific community, that that we had discovered that the universe's expansion is actually accelerating. And if you go back to the Friedmann equations that we were looking at before, in particular at the acceleration equation, I think we showed, yes, that unless the pressure is less than -1/3 multiplied by the energy density, then we would have a decelerating universe. But the discovery then, by amongst other things observing supernovas, was that it seems that this second derivative is actually positive today. So I wanted to discuss a little bit about how that can come about. So in particular, let me discuss a particular case which is called a cosmological constant. So let's consider the following. An energy component of the universe with W, so the equation of state parameter, equal to -1, or equivalently that the pressure is equal to minus the energy density. Now, this is a very strange form of energy. In particular, if we look at the energy momentum tensor, it's going to be rho plus p as usual, u mu, u nu, minus p g mu nu. But for this particular scenario with W equal to -1, rho plus p is 0. So this would be 0, which means that it doesn't matter what the rest frame of this energy component is, or equivalent, it doesn't have a rest frame. Its stress energy tensor is always going to be given by, since p is equal to minus rho, by rho multiplied by g mu nu. So it's always going to be directly proportional to the metric. And it has no rest frame. Furthermore, if you look at the evolution equation for rho itself, we know that rho dot, that was equal to 1 plus W multiplied by rho. So in this case, this is 0, which tells us that rho is constant. This is, of course, where the term cosmological constant comes from. It doesn't matter if we evolve time, if the universe expands or not. Rho dot is 0, so this energy density is going to be constant. And since we had W equal to -1, which was less than -1/3, this is a form of dark energy, which means that we can have an accelerating universe. So if we insert this into the Friedmann equations, we're going to find that this is actually a universe that expands exponentially rather than as a polynomial t. So if we do this, we're going to find that A is e to the h t minus t naught instead. And it's going to turn out that h is, of course, also going to be a constant in this case. So in this case, the Hubble parameter is a constant as well. If we have this type of energy component along with some other energy component while the universe expands, well, this energy component is constant, whereas if you expand the universe, for example, a matter component or a radiation component is going to dilute. which means that eventually this cosmological constant is going to dominate completely. And if it does, the universe expands exponentially, and we essentially end up after some time with a solution that looks something like this. So this can lead to an exponentially expanding universe. Now, if we look at the, and I'm going to take a look at the lecture notes for this. So if we look back, if we actually look at what we observe of our universe today, so let's see where we are. Let's look at this. So I want to concentrate on this figure here. So let's blow that up a little bit. So this is the reference if you're interested in that, but I want to focus here on the implications. So the orange region, the green region, and the blue region here are different observations from different types of experiments. On the x-axis, we have omega m. So this is the amount of matter in the universe today. So it's the energy density in matter divided by the critical density. In the same way, we have omega lambda, which is the energy density contained in a cosmological constant component. So the kind of component I just discussed. This is called the lambda CDM model, where essentially you put two components into the universe. You put one which is a dark energy and one which is a matter component. And then you can look at different observations and see where is our universe. And the things that I want to discuss here is, well, first of all, let's look at the CMB here. This is a measurement of the cosmological microwave background. And it's essentially very parallel to this line that says flat, which is where omega lambda plus omega m is equal to 1, so that the total energy density is 1. And that's essentially because when you look at the CMB, you know more or less how large the scale of the fluctuations in the CMB are going to be. And so that using that, you can essentially draw triangles in your space and check that the angular sum adds up to 180 degrees. And that's essentially why this CMB looks like this. And if you superimpose the measurements of the supernova luminosities, which are going to depend on the expansion history of the universe, that tells you something like this. And the crossing of those two are essentially where our universe is allowed to sit. Then there is this third type of measurements, which is called baryon acoustic oscillations, and I don't really have time to go into what that means, but the conclusion is quite clear just from the supernovae and from the CMB, and that is that our universe is living around here, which is essentially a flat universe because it's on this line where the sum of omega lambda and omega m is 1, and it has a significant, around 70% of the energy density of the universe today is in the form of this cosmological constant, and only around 30% here is in the form of matter. So the observation is that, well, we are basically already dominated by a cosmological constant, which means that a priori, if this is the entire story, then the universe would eventually start going on to this exponential acceleration. So that's one of the possible fates of the universe, that if this dark energy is actually dominating, and if there is nothing else to the dark energy than being a cosmological constant, then the universe will eventually end up in an exponentially expanding state. So that's kind of what I wanted to say about accelerated expansion and the cosmological constant. Are there any questions so far? Okay, so I wanted to leave you all with a final example, well, leave you all, at least those who are taking the smaller course, with a final example. And it is an example that kind of highlights, how you can be fooled to think that just because you have chosen some coordinates, that a space-time is fundamentally different from a different space-time, although they are in fact exactly the same. And I actually think that we will only have time to do this example, and then I will discuss inflation next time or the time after, depending on the time. So a final example. So let's consider the following. Let's consider, we have now talked about the Friedmann, Lemaitre, Robertson, Walker universe. So an expanding universe that has some content. So what I want to discuss is the case where we have an empty universe. So consider an empty universe that is rho is equal to 0. So we have nothing in this universe. So it's essentially a vacuum solution. Then I will have the following Friedmann equation. I have this has to be equal to minus kappa divided by a squared. Or in other terms, since I have a squared here on both sides in the denominator, a dot equal to minus kappa, or a dot squared equal to minus kappa, which is equal to what, some positive constant k squared. But we recognize this. This is for s equals to k inverse hyperbolic sine kr, and it will give us for the scale factor that a is this constant k multiplied by the time t. So this tells us that our universe has a hyperbolic structure. It's a three-dimensional hyperbolic space that expands linearly, because this scale factor grows linearly with this time parameter. So the metric in this case is given by ds squared is equal to dt squared minus k squared t squared dr squared minus t squared, and then this hyperbolic sine function squared kr d omega squared. So this is our metric. Now, what is the curvature of this metric? That's a rhetorical question, and you can answer that if you want, if you know it, but I don't expect you to know it. However, you can compute it. And if you compute the curvature, we get r mu nu lambda sigma equal to 0. So our space has 0 curvature. It has 0 curvature. It is an empty universe. However, it is an expanding universe in the sense that it's given by the it's a Robertson-Walker universe essentially. However, if I have no energy density, I have no curvature. That means that essentially what I'm dealing with is an affine space. It's just that I've written it down in some strange coordinates. And the only thing that I know of that has rho equal to 0 and 0 curvature is Minkowski space. So this these are properties of Minkowski space. The only thing is that it just so happens that, yes, this is Minkowski space, but I have used a rather strange set of coordinates. So, I mean, if you look just at the scale factor a here, you would think that, well, as t goes to 0, a goes to 0. So this means a priori I have some sort of singularity here. But it turns out that this is going to be a coordinate singularity. And I can go back to the standard Minkowski coordinates. So I can let tau be equal to t times the hyperbolic cosine of kr, and I can let chi be equal to t, this hyperbolic sine of kr. If I do this, what I find is that ds squared is going to be d tau squared minus d chi squared minus chi squared d omega squared. So this here is now just Minkowski space written in spherical coordinates for the spatial part. Nothing else. So what it turns out is that this coordinate system, where I obtained an expanding universe, is nothing else than the forward light cone of whatever point t equals to 0 corresponds to. So essentially, if I draw a picture here, I would have something like this. And let me draw the t-axis. So this is the tau axis, and this is the chi axis. And the region that I have these coordinates in are going to be the future light cone of the origin here. So if I draw here the light, oops, that's the wrong. If I draw here the light cone, these coordinates, t and r, are valid inside the future light cone. They're valid inside here. They do not describe whatever is going on out here, but they're only valid in this future light cone. And the coordinate lines of the t coordinate are straight lines originating in this origin. So they are going to be looking like this. These are coordinate lines of the t coordinate. Whereas the coordinate lines of the r coordinate are these hyperboloids, looking something like this. Let's take that instead. So the hyperboloids look something like this. So we can fool ourselves to think that this is a very strange space-time that is linearly expanding. It's just that we have chosen these hyperboloids to be our surfaces of simultaneity instead of the usual convention in Minkowski space to choose surfaces of constant, in this case tau. But it is the same space-time. And the singularity that we had here in the TR coordinates, that's of course a coordinate singularity in just the same way as if you have polar coordinates in two-dimensional Euclidean space, you have a coordinate singularity at r equal to 0. Are there any questions on this example or anything else for that matter? Okay, so Then we are essentially done with what I wanted to say today for the smaller SI course. And next time we will be discussing a little bit about the experimental observations that support general relativity, but that will be a more informal discussion, let's say. And then the last time we will be discussing the entire course. However, I'm not sure that I will finish up with cosmological inflation, which is for the larger course today, but I'm going to start, and then depending on how it goes, I may continue next time as well. So that's all for the SI course for today. I will continue now with the rest of the SH course. So for the SH course, one thing that is included, that's not included in the SI course, is what's called cosmological inflation. And cosmological inflation is essentially, if you look at the standard picture of like the standard Big Bang theory, it has a number of problems. And I'm not going to go through all of them, but I am going to go through a couple of them. And then we're going to see how inflation essentially provides you with a possible solution to this. Again, inflation is still not experimentally verified, but it's a very nice solution to be aware of, and a lot of research is going into this direction still today. So the problems of standard Big Bang. I mean, apart from providing you with this kind of singularity at the beginning of the universe, so two of them are called the flatness problems. So flatness, which is essentially asking the question, if we look at this figure, there is no a priori reason why the universe should be flat. And yet we observe that the universe is indeed very flat. So this is the question, why is the universe flat? Or why is the universe so flat? And then we have the homogeneity problem. Why is the universe so homogeneous? So I'm going to go through each of them to a slightly more detailed extent now. So, but those are the main questions, so to say. So for the first question, the flatness problem, we know from the Friedmann equation. So from the Friedmann equation, we can solve for kappa. Kappa minus kappa is h squared a squared minus 8 pi g rho divided by 3 a squared. So this can be rewritten as 8 pi g divided by 3, and then omega to the power of -1, and -1, then rho a squared. Now, for a universe that is dominated by an ideal fluid, by ideal fluid of W as the equation of state parameter, we know how the energy density behaves. We've seen this already today. So rho is proportional to a to the -3, 1 plus W, right? So this means that if you look at 1 minus omega to the minus 1, this is going to scale as rho inverse a squared, which is essentially a to the 1 plus 3w. So this means that if w here is larger than minus 1/3, then this thing here, 1 minus omega inverse, is going to grow with time, which means that that if you observe a very flat universe today, then omega must have been even closer to 1 at early times. So essentially, and we do observe a very flat universe today. And if we evolve then the universe back in time, the universe must have been very, very, very close to flat at an earlier time. So we kind of have to fine-tune the starting conditions in terms of energy densities in the universe to have this flat universe. So that's the flatness problem. Why is the initial density in the universe so close to the critical density? The second one is that the homogeneity. So if you look at the CMB, and I'm going to try to draw a picture here again. So I'm going to put T equals to T CMB here. So this is when the CMB is released. And then I'm going to draw it an earlier time, which is T equals to 0. So this is where we have the singularity of the Big Bang. If I draw the light cones here, the past light cones, if I take this point and I draw the past light, I don't know how it's going to be, but I can compute how it's going to be given that I take the same sort of evolution backwards in time. So if I do this, then at those 2 points in space, they have completely disjoint histories because their past light cones are completely disjoint. So they are not in causal contact with each other. So a priori, whatever initial conditions I would have here, and whatever initial conditions I would have here, these 2 points would be dependent on completely different initial conditions. So a priori, if I look at the cosmic microwave background, there is no a priori reason why I should have the same temperature here and here. But if we look at the CMB, it is indeed very homogeneous. It's homogeneous to within 1 part in 10 to the 5 or something like that. So the question becomes, if now these 2 events are dependent on completely different initial conditions, why are they the same temperature? And the solution to both, well, a possible solution to both of these problems is what is called cosmological inflation. So the solution, cosmological inflation. So the question is, what is this cosmological inflation? So essentially what I'm going to do is that I'm going to introduce, in the early stages of the universe, I'm going to introduce a rapid growth of the scale factor in the early universe. So long before the release of the cosmic microwave background, I'm going to introduce essentially an exponentially expanding universe. So with W less than minus 1/3, so we're going to have an accelerated expansion there. So the question then is how would this solve the flatness and horizon problems? So the flatness, well, we had this 1 minus omega inverse, which was proportional to a to the 1 plus 3w, this now shrinks with time. As long as this accelerated expansion dominates. So instead of growing away from having exactly the critical density, this universe is pushed towards having close to critical density. So whatever my initial conditions were, if I let this period of rapid growth last for long enough, I am going to end up with essentially what is a flat universe. When it comes to the horizon problem, so when I evolved back in time and I did not have this, the light cones looked like this. However, if I have this this rapid expansion instead, what I'm going to have is that the horizons are going to expand more or less like this instead. So I'm going to get something like this instead. So on the scale that I can see in the cosmic microwave background, all of the events within the cosmic microwave background are going to be dependent on the same initial conditions instead. So what was not in causal contact without this period of rapid expansion are now in perfect causal contact and have time to enter into equilibrium, and therefore in the end be observed to have essentially the same temperature. So the horizon problem is solved by allowing causal contact or common history for events in the observable universe. So rather than having only very close by points in the CMB having a common history, we have that all over the sky, the points of the CMB that we can see would be in causal contact initially and would have been having a common history and could therefore have the same temperature without imposing that the initial conditions here and here have to be the same. Are there any questions? Okay, but there is now a problem. So this is the basic idea behind inflation, but the problem becomes, how do you stop it? Because if you look back to what we were discussing when we were discussing accelerated expansion, well, we saw that rho of the dark energy in this case was constant, whereas everything else, all the matter components, all the radiation components, they are diluted as the universe grows, and the universe grows very rapidly when you let dark energy dominate. So the problem is, how am I going to stop this expansion if I have this type of accelerated expansion in my universe? Because a priori, if you just set the equation of state parameter to some fixed number, then that fluid is going to dominate forever. So the solution to this is to make dynamical, is to make the inflation dynamical. That is, we insert something into this universe where the equation of state parameter is going to change over time. And one of the more common examples of this, I'm just going to go through this example, is something that's called slow roll inflation. This is just to give you an idea of how an inflationary model can look like. So, and you're going to be kind of familiar from the homework with what I'm going to do now. So the idea here is that I insert a scalar field. So consider a scalar field phi that's homogeneous, because if it was not, I would break the rules of cosmology, because it would be different in different points. It's homogeneous, and it depends only on the time coordinate t. And it has Lagrangian density, L, given by exactly what you got for the homework problem. So 1/2 g mu nu d mu phi d nu phi minus some potential v of phi. Now, you know what the stress energy tensor for this is, because you computed it in the homework problem. If you don't know, it's in the suggested solutions. So we find that T mu nu, that's going to be d mu phi minus g mu nu, g nu, not nu, lambda sigma, divided by 2, d sigma phi, d lambda phi, minus v of phi. So that's our stress energy tensor. So if we go through everything now and we compute T00, going through all of the motions, we find that this is phi dot squared over 2 plus v of phi g00. And we find that Tij, that's going to be Gij v of phi minus phi dot squared divided by 2. So, as we said, with the 4 velocity now, so u0 is equal to 1, and ui is equal to 0, because we cannot have an ideal fluid that moves essentially with respect to the co-moving frame. Then we find that T mu nu is equal to v of phi minus phi dot squared divided by 2 times g mu nu plus phi dot squared u mu u nu. So we can here identify this is minus p, and this is the energy density plus p. So we can identify from here the pressure, and once we have the pressure, we can from this identify the energy density. So this implies that the equation of state parameter is going to be given by phi dot squared minus 2v of phi, so this is essentially the pressure, divided by phi dot squared plus 2v of phi. So now the special case is if the field is not changing much with time and the potential is much larger than this change. So if V of phi is much larger than phi dot squared, then this is equal to -1. And you recognize that if the equation of state parameter is -1, then we essentially have the situation where we have this cosmological constant. And this is going to lead then to this accelerated expansion in the early universe. So as long as this holds, I am dealing with what is essentially a cosmological constant. However, we can also write down the equations of motions for phi. I'm not going to do it in detail. It's in the lecture notes. What I will find is that I got phi double dot plus 3h phi dot has to be equal to minus v prime of phi. So this looks somewhat like a harmonic oscillator, just with, or rather like an oscillator with some friction term. This term is often referred to as Hubble friction. But the point is that as long as this acceleration is small, this means that for small phi double dot, this means that I can solve for phi dot that's going to be equal to minus v prime phi divided by 3h. And remember, as long as I'm in the cosmological constant phase, this h is constant as well. So what can give us then this kind of solution where we keep this to be the case in the early universe, and then eventually I move on to something else? So the kind of potential that we would be looking for is a so-called slow roll potential. So we would have something like this. So we would have the potential here on the y-axis, and then we would have the field value on the x-axis. So I'm going to look at a potential that might look something like this. So what would happen would be that since the derivative of the field is given by this, so it's given by essentially the derivative of the potential itself, having this much smaller than that is going to depend on the potential. So if I have the derivative here small, so in this region, the derivative is small. So this means that if I start out over here, where the derivative is small, we're going to slowly move in that direction. And as long as I'm doing it slowly, which is again given by this condition together with that, I'm going to have a universe that expands exponentially because of this equation of state parameter. However, eventually, I will come to this point where my field starts moving faster, and I exit this slow roll. So this is the exit of slow roll. The slow roll regime. So once I get to this regime, I am no longer in a scenario where the universe is accelerating exponentially. And that's good, because that means that eventually this accelerated expansion ends, and the idea, just to get the general idea what's going to happen here, is that as the field rolls down here, we have the Hubble friction term. So this field is going to kind of start oscillating around the minimum and eventually end up at 0 here, or at the minimum level. So what can happen in this case is that the energy density that was created because once inflation ends, all of the energy density is going to be in this field phi. So let me just mention that phi is called the inflaton field here. So all the energy is going to end up being in phi. Once we start oscillating here, this energy through this friction and through a process known as reheating is going to go from the inflaton field to repopulate all of the matter fields. So the electromagnetic field, any other matter field that we might have, and thereby creating the contents of the universe as we know it today. Because after inflation ends, since I had this exponential expansion, the universe is essentially going to be void of anything else than the inflaton field. So down here we have reheating, which means that we introduce again into the universe what we see in the universe today, such as matter and radiation. And then, of course, once the inflation is ended and we have had this reheating process, then we enter into the standard Big Bang scenario. Let me just mention that this is one possible inflation model. There are many others, but it's just so that you can see an example of it.